Hi my dear viewers. So we are going to discuss the Pearson Edexcel IAL Chemistry Unit 3 paper, which is of Jan 2025. So if you need any support or if you need any tutoring for either physics, chemistry or mathematics of IGCSE or IAL, you can contact me on +94 773 755 757. Alright. This question is about qualitative testing for ions. The student was given a solid sample of potassium sulfate. Describe how the student could use the flame color to confirm that the solid sample contains potassium ions. Outline the experimental procedure stating the color change, stating the color of the flame produced. Right. So here on this question, you have to specifically mention how we do the flame test. So first thing is you have to take the nichrome wire. You have to get a nichrome wire and dip it inside hydrochloric, and then place it on the Bunsen burner, uh, so that if there was any color remaining, that has to be given out. Then when we are sure that there's no color given out by the nichrome wire, then you have to get the nichrome wire and dip it again in hydrochloric, because the whatever the metals which are giving flame colors, though all those things, the metals cations, they are soluble in chlorides, they are soluble. So we dip it in hydrochloric again, and then you dip it in the whatever the required sample, as they have sent the potassium sulfate, then place it again at the Bunsen burner. So when you place it at the Bunsen burner, Bunsen flame, it will have to give lilac color. Lilac is the color characteristic for the potassium. Alright, we'll move to the next question. The student dissolved some of the solid sample in deionized water in a test tube. To the test tube, the student added diluted hydrochloric acid followed by barium chloride solution. A precipitate was observed. Given the color of the precipitate and the ionic equation for this formation, include state symbols. So they say barium is there. Here there is a sulfate. So we know that barium sulfate is a precipitate. So I assume that's what they expect. So then we have to move to, I'll write the answer for that part here. So barium ions, it's barium 2 plus, it's the aqueous. They say to include the state symbols also. Uh, Sulfate ions forms barium sulfate, which is a solid. So they are asking what is the color of the precipitate. We know that this is a characteristic test for the sulfates, which is white in color. So the color of the precipitate is white. Another student was given a solution containing one type of cation and two types of anion. That means one positive ion and two negative ions. The student warmed some of the solution in a test tube before adding aqueous sodium hydroxide and holding Dan Lebrin's paper at the mouth of the tube. From the results, the student identified the cation as the ammonium ions. So we know that when you placed ammonium, when you have ammonium ions, when you have ammonium ions, for that when you add a hydroxide, it gives out the gas ammonia. When ammonia is given, uh, when we take a red litmus paper and place it near the gas, it will turn blue color. So that's what you have to explain here. To another test tube of the solution, the student added silver nitrate solution. A pale yellow precipitate was formed. If it is white color it's chlorides, if it is pale yellow it's bromides, and if it is yellow usually it's iodine. The student then added an excess of diluted nitric acid. Efference was observed. Efference means the gas is evolved. So some of the precipitate dissolved. The student added an excess of concentrated ammonia solution to the remaining precipitate. The precipitate dissolved to form aqueous solution. Complete the table about the student's results. So obviously the formula of the gas evolved. Now we'll see what the substance is. Alright. The student added an excess of dilute nitric acid and difference was observed. So when you place acid when a gas is given, most probably the gas given out is carbon dioxide, and the ion which was there in the solution uh, can be a carbonate. Formula of the precipitate that dissolved in nitric acid. Yeah, it has to be there is sodium ions, I guess, sodium or potassium. It's potassium ions. Potassium carbonate is not a precipitate because group 1 metals, they all the carbonates they are soluble, so it can't be potassium. So the previous part they said silver nitrate is added, so definitely it has to be silver carbonate. Silver carbonate Ag2CO3, which was the thing which gives out carbon dioxide gas. They say the precipitate the student added an excess of nitric concentrated ammonia solution. So the precipitate dissolved into form a colorless solution. This is a test to confirm the halides. If it is dissolved, it's what? It can be bromide, and if it is not dissolved with even concentrated ammonia, it's an iodide. So this has to be what? Silver bromide. The precipitate, precipitate which was dissolved in a concentrated ammonia has to be silver bromide, AgBr. Alright, go to the next part. Question number 2. The student uses the reaction of a magnesium with hydrochloric acid to determine the volume of 1 mole of hydrogen gas at room temperature and pressure. So they have given magnesium plus hydrochloric reaction forms magnesium chloride plus hydrogen. They have set the procedure. Weight 0.303 grams of magnesium ribbon at approximately 25 centimeter cube of 2 moles per decimeter cube hydrochloric acid into burette and carefully add 25 centimeter cube of water on top. Push the magnesium ribbon into the open end of the burette so that it stays in position. Quickly invert the burette. Clamp the burette vertically and take the burette reading. Wait for the magnesium to start reacting. Take the final burette reading after all the magnesium has reacted. A diagram of the experiment is shown. So you have a burette. After the reaction is made to happen, maybe a gas is evolved. To collect the gas, maybe you are inverting the burette on opposite side so that the top part the gas will be collected. Right. We'll move to the next page to see what they're asking. Explain why the volume of hydrochloric acid added to the burette in step 2 does not need to be exact. You must include a calculation. Right. That most probably this has to be to confirm that hydrochloric has to be in excess. So we'll have to calculate the number of moles of hydrochloric and the number of magnesium, and to show that the after the now it's 1 is to 2 reaction. The stoichiometry of magnesium to hydrochloric is 1 is to 2. We have to show that hydrochloric in excess. We'll see how we do it. Alright, we'll start to find the number of moles of the acid, and we'll try to find the number of moles of the metal also. Okay. All right. So the right. So they have said the mass of magnesium is 0.03. So to find the number of moles, we need the equation n equals simple M over capital M. So 0.03. I think the molar mass of magnesium has to be 24. They have given periodic table. Check that out. Yes, magnesium 24.3. We'll take it. We'll take the value they have given exactly, right? I hope all of you saw that magnesium is 24.3. Okay. So uh, 0.0403 divided by 24.3 will give the number of moles of magnesium. So it's 0.03 divided by 24.3, which I'll get as 0.00123. 0.00123 moles. So if I check the number of moles of hydrochloric, now if this is the number of moles of magnesium, understanding the point that magnesium is to hydrochloric, the stoichiometry is 1 is to 2. Therefore, the number of moles of hydrochloric required will has to be twice of what you got found, which is I hope you see it 0.00123. I'm sorry about the mess here. This is 0.00123. 00123. So 0.00123 has to be multiplied by 2. So you can use the calculator and do it. 0.00 246 moles is required, right? So they say in the question 25 centimeter cube of 2 mole per decimeter cube hydrochloric is carefully added, right? Right. Added, carefully add murate and carefully add 25 centimeter of water on the top. So if I find the number of hydrochloric added, it's C equals NOV. So I get N equals CV. So N is equal to concentration is 2, volume is 25, divided by 1000, 4 into 10 to the power minus 3. So I get 50 into 10 to the power minus 3, which is 0.2 into 25 divided by 1000, which is 0.05. 0.05 moles. So we can see that now the required amount is 0.00246 and you have 0.05. So compared to 0.05, 0.00246 is smaller. Therefore, you can say HCl is in excess. Right. Explain why the volume of hydrochloric acid to burette does not need to be exact, because it's in excess, so it does not need to be exact. So it does, you don't need to have exact amount because it's in excess. State why magnesium does not start reacting uh, as uh, as the burette is inverted in step 4. So we have to say now, as you saw the diagram, it takes some time for the hydrochloric to react. So first hydrochloric has to fall down, then afterwards only what it would react. So there is enough time for hydrochloric to come down, so therefore it will not react. Initially what is touching with the magnesium strip is water. So if you say that, you have to get marks. Initially magnesium is touched by its water. Water takes time for hydrochloric to reach the magnesium strip. Move to the next part. The diagram shows the burette readings from step 4 and 5. Burette reading from step 4 is initial reading. Burette reading from step 5 is the final reading. So record the burette readings and hence the volume of the hydrogen gas produced in the experiment. So usually if you are doing this paper, it's always better if you can invert the paper, because then it would be easier. We'll see how, otherwise what you have to read it in this way. All right, so we'll get the reading. Now I can see 45, 46, 46.1, 46.2, number between 46.2 and 46.2 to 46.3. So initial reading on the burette would be 46.25, right? So 46.25, and the next instance it's 10.1 2 3 4 5 6 7, 10.7. So the readings I'm getting are 10.7, I'm sorry, yeah, 10.7 and 46.25. So from I can't 46.25, I can't subtract 10.7 minus 4625. It's 4625 minus 10.7, isn't it? 10.7. So when I subtract, I get 35.55. Unit reading in step 4 will be 46.25. Unit reading in step 5 is 10.7, and volume of hydrogen gas is the difference between them, where the gas has got collected at the top of the burette, which is 35.55. Right. Calculate the volume of uh, 1 mole of hydrogen gas at RTP in centimeter cube using your answers to part C. Uh, the reaction equation and the mass of magnesium 0.03 used in the procedure. Right. Okay, we'll see how we are going to do this. So this is the volume of hydrogen. So I'll write this as VH2. VH2 is this. So we know equation N equals uh, V over Vm. So they are asking to find the volume of 1 mole. That means they are asking what is Vm. So Vm is equal to V over N. They are asking it the questions answer in centimeter cube. So yeah, the volume is 35.55 centimeter cube. The number of moles is uh, 0.03. Yeah, we found the number of moles of magnesium before, I guess. The number of moles of magnesium was 0.00125, I guess. Yes, 0.00125. So the molar volume will be 35.55 divided by that answer. So we get 35.55 divided by 0.00125, which is 28,440. 28,440 centimeter cube. Right. State why magnesium does not start reacting as soon as the burette is inverted in step 4. They are asking why is it not reacting just as it was inverted. So initially when you do it, magnesium is not in contact with the hydrochloric. So all of a sudden it will not react, but after some time, bit by bit, it would react, right? I think we did this part, isn't it? I'm sorry. Right. Okay. The magnesium ribbon used in step 1 contained magnesium oxide impurity of up to 2% of by mass. So it's not fully magnesium. Part of it is magnesium. The rest is magnesium oxide. According what they are saying, 2% is magnesium oxide. So 98% is only magnesium. Explain whether these magnesium oxide impurity could account for any difference in your answer to D from the data booklet value of 24,000. So the thing is, as we did here, I'll show you the workings. Uh, N equals, sorry, molar volume. Molar volume Vm is equals to uh, the volume of the gas divided by number of moles of magnesium, where I can write it as volume divided by number of moles. The number of moles is equals to mass over molar mass, isn't it? So mass over molar mass. So I can write it as P into capital M over simple M. So whether this magnesium oxide impurity could account for any difference in your answer. Uh, yes, we assumed it was fully magnesium, but actually it's some part is magnesium oxide. That means the number of mass of magnesium will be lesser than what we actually expected, even though we did the calculation. So looking at the equation, we understand when the mass of magnesium decreases, the molar volume would increase. So the answer what we get will be higher than what the amount what we got before. That means the molar volume, the answer will be getting is actually higher than what it is. So it was 24,000, but we got what? 28,440. We got it higher because of this. The mass of the actual mass of the magnesium oxide was lower than the amount what we thought of. Two readings were taken to measure the mass of magnesium used in the experiment. The uncertainty in the reading was 0.0025. So they are asking calculate the percentage uncertainty in the mass of magnesium used in the experiment. So in this question they have said they didn't say the reading is 0.0025. They said the uncertainty is this, because if it was a reading we have to divide it by 2, but because it's the uncertainty we don't have to divide by 2. That's the first thing you have to understand. Next thing is uh, they say two readings were taken, so that means the uncertainty has to be multiplied by 2. So then when we are finding the percentage, when we are calculating the percentage uncertainty, so it's 0.0025 into 2 divided by the reading. The reading of magnesium was, which is the mass of the magnesium, which was 0.03. So 0.03 multiplied by 100 will give the percentage uncertainty. So we'll enter on the calculator how we, and see how what's the answer we are going to get. 0.0025 multiplied by 2 divide by 0.0, sorry, divide by 0.03 multiplied by 100. The answer I'm getting is 16.666. So when I round off to 2 decimal places, I can write 16.67%. Alright, we'll move to the next part of the question. Right. The student wanted to um, reduce the percentage uncertainty by using double the mass of magnesium. Give the reason why the experiment outlined in the procedure could not be conducting successfully using double the mass of magnesium. So, as we remember, the volume was closer to 24 centimeter, 24 decimeter. I'm sorry. Uh, we got the volume of the yeah, the volume collected of hydrogen was 35.55 centimeter cube, isn't it? So a burette will have a reading of maximum 50. So if we take twice the mass, that means the volume of gas produced will be twice, which will be it was 35.55, so somewhere closer to more than 70. 35, yeah. So 70 cannot be read by a, what do you say, burette, which is 50 centimeter cube. A burette is usually 50, so you can't get a reading. You can't measure the volume using a burette. The burette, compare the size of the burette's volume, the volume of gas produced is higher, therefore we can't read. That has to be the answer. Right. Question number 3. The concentration of a solution of barium hydroxide can be determined using a standard solution of uh, ethane dioic acid. State what is meant by the term standard solution. So simply if I talk, standard solution are solutions what, which are stable, so which does not absorb water or does not react, and you have to have this word definitely. The concentration is known. Concentration uh, is accurately known. The accuracy is a must. You have to know it really accurately. Accurately known. Right. Describe the preparation of 10 centimeter cube of 0.05 moles per decimeter cube standard solution for ethane, uh, ethane dioic acid, starting with the crystals of ethene dioic acid dehydrate H2C2O4.2H2O. The answer should include the details of the apparatus used and the mass of H2C2O4.2H2O required. Right. We'll try to do a calculation to see how much of the mass of the acid is required. Okay. All right. First, we'll start off with they have given the volume as 100 centimeter cube and the concentration as 0.05 moles per decimeter cube, and with this you can find the number of moles. C equals NOV, so N is equal to CV, so which is 0.05 multiplied by 100 into 10 to the power minus 3. I multiply by 10 to the power minus 3 to convert centimeter cube to decimeter cube. So I get 0.05 into 0.1, which is 0.005. You don't have to think about this or do this because you are given a calculator. Use a calculator to get the answer. Right. So they are asking the mass, isn't it? So N equals simple M over capital M. So capital simple M is equals to N into capital M. So number of moles is found 0.005. We have to know the molar mass of the substance. So hydrogen has a atomic mass of 1, so it's 2 into 1, and oxygen has 12, so 12 into 2 plus hydrogen has 16, 16 into 4, and water, hydrogen has 2, oxygen has each hydrogen has 1, so there are 2 hydrogens, which is 2, and 1 oxygen, which is 16. 16 plus 2 is 18. So I will multiply 2 into 18. So then I get the answer as 2 into 1 is 2, 12 into 2 is 24, 16 into 4 is 64, and 2 into 18 is 36. So 24 plus 64 is 88, 88 plus 2 is 90, 90 plus 30 is 120. So I get the answer here as 126. So then uh, the number, the mass required will be 0.005 into 126, isn't it? Yeah. Yeah. So we'll enter on the calculator and see what the answer is. 0.0005 multiplied by 126, which I get it as 0.63 grams of what? Magnesium. So we did the calculation to find out how much is required. Now they say describe the preparation. Your answer should include the details of the apparatus and the mass of what is required. So we found the mass. Now we have to explain how we have to do the step. So we found the mass, which was 0.63 grams. So we have to use a volumetric flask, and this particular substance, whatever we get it onto petri dish, we have to wash it off onto the volumetric flask using distilled water, and afterwards we have to completely transfer the the solid, as I told, from the petri dish to the volumetric flask until the mark is 100. So we have to transfer the liquid as such. The volumetric flask has a 100 centimeter cube what do you say reading. So until that you have to fill up with distilled water. So I'm not writing the steps. I hope you understood. All right, moving on to part C. 25 centimeter of 0.05 ethanoic acid H2C2O4 was added to a conical flask and titrated with barium hydroxide solution of an unknown concentration. Name the piece of apparatus that should be used to add the ethanidioic acid solution to the conical flask. So they say it's a 25 centimeter cube, right? So we need a pipette which is 25 centimeter cube. The titration was carried out with a few drops of phenolphthalein indicator in the conical flask. State the color change observed at the end point of the titration. So it's ethanidioic acid was added to a conical flask and titrated with barium hydroxide. That means initially what you have is acid. Afterwards, what it becomes neutralized, and yet if you continue, what it becomes alkaline. So it's acid to alkaline. Which is colorless to pink. That's the color change for phenolphthalein. The formation of white precipitate was formed during the reaction, suggests the identity of the white uh, precipitate by name or formula. Now C2O4 is there, barium was added, so barium oxalate BaC2O4 has to be the equation of the precipitate which is formed. Right, we'll move on to part 4. All right, so the titration was repeated, giving a mean tite of 31.55 centimeter cube. Calculate the concentration of barium hydroxide solution in grams per decimeter cube. So they have given the ratio of barium hydroxide to H2C2O4. That's the stoichiometry, which is 1:1. Yeah, we'll try to do the sum. 25 centimeter cup 0.005 ethanoic acid was added to a conical flask. Okay, so I draw the conical flask. So this is acid. 25 centimeter cube 0.05 m, and when it was titrated it was barium hydroxide, and they have set the volume of it as 31.55. Right, for the acid I'll try to find the number of moles. So we have the equation C equals NOV, so N is equal to CV. So the concentration is 0.05, volume is 25 into 10 to the power minus 3, or in other words 25 divided by 1000. So we'll enter the whole thing on the calculator. 0.05 multiplied by 25 divided by 1000 equals 0.00125 0.00125 moles. Right. So the same amount of moles has to be there on barium hydroxide, as they have said 1:1. So number of moles of barium hydroxide also has to be the same, which is 0.00125 moles. If I apply the equation C equals NOV, the concentration will be 0.00125, and they have set the volume as 31.55, which has to be multiplied by 10 to the power minus 3, right? So yeah, I'm dividing the the volume which is in centimeter cube by 1000 to convert into decimeter cube. So the answer I'm getting is in moles per decimeter cube. So when I get the answer in moles per decimeter cube, I have to multiply it by the molar mass of barium hydroxide to get it in grams per centimeter cube. First we'll get this answer and see. This divided by 31.55, which will be 0.0396 moles per decimeter cube. So we need in grams per decimeter cube. So we have to use we have to multiply by the molar mass. So it is 0.0396 multiplied by barium hydroxide. We find the relative atomic mass of barium. Barium. Barium is 137.3. I hope all of you see it, right? So 137.3. So barium hydroxide is 137.3 plus barium hydroxide BnOH twice. Oxygen is 16 plus 1, that whole thing into 2, right? So yeah, I'll multiply 2 into 17. 2 into 17 is 34, isn't it? So what I get is 137.3 plus 34 has to be multiplied by 0.0396, right? It's 2 into 17. 2 into 17. For that I have to add 137.3. You get 171.3. I have to multiply that by 0.0396, right? I get 6.78. 6.78 grams per decimeter cube. Right. Right. That's the end of that question. Right. We'll move on to question number 4. This question is about preparation of 2-chloro-2-methyl propane from 2-methyl propan 2-ol and concentrated hydrochloric acid. Right. So what they are doing is they are converting alcohol into a haloalkane, isn't it? Right. The procedure: pour 9 centimeter cube of 2-methyl uh, 2-methyl propan 2-ol into a separating funnel. Add 20 centimeter cube of concentrated hydrochloric acid to a separating funnel about 3 centimeter cube at a time. Stopper and invert the funnel after each addition. Discard the aqueous layer before washing and washing the organic layers repeatedly with sodium hydrogen carbonate solution, releasing the pressure after each addition. Transfer the organic layer into a small dry conical flask and add 3 spatula measures of anhydrous sodium sulfate, swirling the flask after each addition. Decant the organic liquid into a pear-shaped flask and distill the 2-chloro-2-methyl propanone into a pre-weighted conical flask. So I guess they say uh, anhydrous sodium carbonate, sodium sulfate. So anhydrous. When I see the word, I feel that this sodium sulfate is added to what? Remove the water or the moisture. And we'll see. Give one reason related to safety. Why the hydrochloric acid is added to the separating funnel 3 centimeter cube at a time and not all at once in step 2. So hydrochloric acid is a very highly reactive acid. It's a strong acid. So all of a sudden the solution will get heated. Oh, and there might be a pressure build up. So to get rid of that, maybe they are using this without adding the whole thing, adding step by step. Right. Part B. Draw label diagram of the separating funnel at the end of step 3. So they have given the what you say the density of the uh, haloalkane, which is 0.8, 0.85. Density of water is usually 1 gram per centimeter cube. So what I feel we have to understand is that this is lesser than the water. That means what? This might be floating and the aqueous layer has to be at the bottom. Alright. So I'll draw a separating funnel. It up here. So there has to be two layers. This has to be the aqueous, which is with water, and this has to be the organic, which is the haloalkane. 2-chloro 2-methyl propane. Yeah, because its density, the organic layer's density is lower, and the water's density is 1. This organic is having a density of 0.85. Water is have the density of 1. 1 is higher than 0.85. So aqueous layer has to be at the bottom, and organic layer has to be on the top. Sodium hydrogen carbonate solution is added to remove acid impurities in step 4. Give the reason why strong alkali such as sodium hydroxide solution should not be used for this purpose. Now what we are doing is we are we are having alcohol and we are going to convert into haloalkane. So when we add a strong base, what happens is the OH will go and replace the halogen and will again form the alcohol. To not happen that, to avoid that, that might be the reason why they are not using a strong alkali. State the role of sodium sulfate in step 5. So in step 5 they say it's an anhydrous substance, isn't it? Yeah. So transfer the organic layer to a smaller dry conical flask and add 3 spatula measures of anhydrous sodium sulfate, swirling and flask after each addition. So there is water which is formed. We don't need the water to dry it or remove the water. We use the anhydrous which gets hydrated. In that way, it removes of the water. So that might be the reason. That is the reason where they add sodium sulfate in step 5. Identify two changes that must be made to the apparatus shown before distilling in step 6, giving a reason for each change. So I see that the direction the water is moving is wrong. So if you send the water from the top and when it falls off from the bottom, there is no time for the water to stay there. So you can't remove the heat. So that's one mistake. So I have to say the water has to be sent on the other direction. So reverse the direction of water flow, and if they are asking the reason to make the water to stay for longer time, so that it needs enough time which fills the condenser, and the cooling process will happen much more efficiently. The change 2, they're asking what is the next thing to do. Near the still head it's just open, it has to be a closed, uh, and there has to be a thermometer. So we better to say using a stopper or a seal fixed with a thermometer. We use a thermometer as such. We will not exceed the boiling point of the what haloalkane, so that we are sure that the amount what we are at the end collecting at the conical flask is the haloalkane. Right. Calculate the mass of 2-chloro 2-methyl propane produced in this procedure. If the percentage yield is 70%. Right. We'll try to do that part also. Right. So I'll write the balance equation before I start off with it. So it's alcohol plus HCl forming the haloalkane and water. So they say 9 centimeter cube. So the volume of this is 9 centimeter cube. Uh, and yeah, that's all what they have given here. Right. So they have given the density of uh, 2-methyl propan 2. That's the alcohol. So if the density is given, density equals mass over volume. So mass is equal to density into volume. So substituting in that way, I can substitute 0.78 into 9, which will give the mass in grams, doesn't it? So I'll get 0.78 into 9, which is 7.02 grams. So if I know the mass, I can find the number of moles, isn't it? N equals simple M over capital M. So 7.02 is the number of the mass of it. The molar mass of the alcohol is molar mass of 2-methyl propan 2-ol is 74. So I have to divide by 74. That will give the number of moles. So I see that the alcohol and the haloalkane have a ratio of 1:1. So the same number of moles of haloalkane has to be produced. So if I know the number of moles, they're asking the mass, right? To find the mass, I have to use the equation n equals simple M over capital M. Yeah, simple M is equal to simple N over into capital M. So number of moles is known, 7.02 over 74 into molar mass of the haloalkane is 2-chloro-2-methyl propane. Yes, the question has said it has 92.5, and they have said the percentage yield is 70%. That means what? You have to multiply that by 70 over 100. So we move on to the steps. 7.02 divide by 74 multiply by 92.5 uh, into 70 over 100. I can write it as multiply by 0.7, isn't it? So I get it as the mass is 6.4125 6.4125 grams. I divided it by 74, then that answer I multiplied by 92.5. That answer I multiplied by 0. Uh, 0.7, isn't it? Oh, yeah. I hope you understood everything. If you have any doubt, uh, you can ask children. And if you have any questions related to chemistry, physics, or mathematics of Edexcel, IGCSE, or IAL, you can contact me. Have a nice day, dear viewers. Hope you understood everything. Alright then, bye bye.